Alright, hello everybody, and welcome to the Quiz 2 practice problems. I'm going to be going through these problems. There are questions for regular chemistry, and then afterwards there will be just for scholars and honors, and then finally just questions for honors chemistry, based off of what we have learned. So I will tell you when we're moving on, so that if you are in regular chemistry or scholars chemistry, you will know when to stop watching the video. Alright, so we're going to start off with graphing. Something that everyone's gone over. Um, and I want to really focus on this chapter to just understand data and information. And you're going to be seeing this on the quiz. For the regular chemistry folks, this is entirely what we are working on. So, here is our graph. The students who worked ages 14 to 18. The purpose of this graph. First step, always say step 1. Read the title. Most times, this will tell you. I need to erase. Spelled title wrong. Read the title. This will tell you, most times, what you were looking for. The purpose of this graph is quantifying how many students worked ages 14 to 18. So, it is comparing how many students did work and how many did not work at each age. Our y-axis. Here's our second step. Step 2. Read the axis. And I'm going to ask you questions very similar to this. What is the purpose? What is the axis? And then some kind of question like question 3. What is the y-axis? So our y-axis is the number of students. Right? Number of students that either A, worked or did not work, and their age. That's our x-axis. So, but the y-axis is just the number of students. How many 17-year-olds are there in total? Why did that only cut off? That's weird. Step 3. Read the question. Be thorough with this. A lot of times, a lot of the mistakes that I've been seeing has been rushing through the question. You're not reading what the question is trying to ask you. I'll ask, what is the x-axis? You will give me the x and the y-axis. I don't want that. If I'm only asking for the x-axis, all you need to know is the x-axis. So let's go down. How many 17-year-olds are there in total? Well, let's go to our 17. We only care about this subset of data. Only the 17-year-olds. We don't care about the rest of this graph for this question. Now, we have students that worked and did not work. I asked for the total amount of 17-year-olds. So to get that, you would add the two numbers. So if we go from here on over, I would say this is about 6. So 6 of these students did not work. And if we go over here, I would say that's about 19. Approximately. If you gave me 18, if you gave me 7, that's fine too. But I would say approximately 6 and approximately 19. So 6 did not work, and 19 did work. 6 plus 19 equals 25. Now, this is the hard question. I'm going to clear off here. Which of the following pieces of information, if true, would help explain this data? So, what you have to do when you have a question like this, you have to read every single one of the 4 answers and think about what would happen if that was true. So you have to go through all of them. Go back to our data. So, A. It is illegal for anyone under the age of 16 to work except for certain instances. So if this was true, and I'm going to... do I have a way to type in here? I'll type it down here. If this was true, then there would be very, very few students working under age 16. Except for certain instances. There would not be zero. Certain instances means that there are a small amount of students that work under the age of 16. We go to our data, and we can see this. There are very few students that are working under the age of 16. I would say that's 1, and that's about 3. So only 4 students under the age of 16 are working. That seems like a pretty good answer. Let's go through everything else just to double check as well. Local companies are desperate enough for work that they will hire 15-year-olds. So if this was true, I'm going to actually get rid of some here so I can fit this all on one page. If this was true, you would see a lot of 15-year-olds working. If companies were so desperate that they would hire 15-year-olds, wouldn't we see a lot of 15-year-olds working? But again, we only see 3. We only see 3 or 4, it's not as clear, 15-year-olds that are working. That does not line up with what we would say if that was true. So it does not be. C. 18-year-olds are paid more than 14-year-olds. Now, the reason that this is not true, you would see information about pay. Nowhere in this chart do we ever talk about money. It is only, did they work or did they not work? We do not have enough data for this to make sense. This very well may be true, but we don't know this. This is not shown in this graph. Nowhere does it mention the pay. Lastly, 14-year-olds have less homework after school and thus have more time. If they had more time, they might be working more. If a 14-year-old had more time, that time might be spent at a job. We don't see that because we only see one 14-year-old working. We see a lot of the older students that are working. So our correct answer, the one that fits the best in this instance, would be A. I'm going to highlight it here twice. Alright, moving on to our second graph. Here is a temperature versus pressure graph. Now, this does not have a title. We're actually going to see this graph later on this year, I believe. But I do want to kind of go through it. So what this tells us right here, we see our temperature. This is our x-axis. It tells you the temperature, and it gives you the unit. So many times I have seen us forgetting units. That is so important. And I want you to always include the unit. If you do not include the unit, well, what measure of temperature are we talking about? We're talking about Celsius. We're talking about Fahrenheit. In this instance, we're talking about Kelvin. In Kelvin. Our y-axis tells us what the pressure is. Now, we have not learned pressure. It's not something that we've learned yet. We're going to later when we get to gases. But you don't need to know anything about what pressure is to answer these questions. I'm going to make sure of that. But our y-axis is the pressure, and in the parentheses here, our unit is this ATM, which is actually atmosphere. It depends on the atmospheric pressure, but we'll get to that. Alright? You don't need to know what an ATM is. You just need to know that's your unit. That's all you need to know. Our question here. Suppose you had water with a temperature of 300 Kelvin and a pressure of 2 atm. What phase of matter would it be? Now, this graph actually has a really, really weird scale here on the pressure side. We start at 0.0006. This amount from here to here is 0.006. This amount is 0.994. And then this amount is 217. The scales are really weird. Even down here, it's similar. 273. All the way, this is only 100 Kelvin increase. This is a really weird scale. Still though, this is still enough information to answer the question. You just have to be careful with what you're looking at. We'll clear our selection off. So 300 Kelvin and a pressure of 2 atm. So first, let's find 300 Kelvin. Now, this scale is weird. Absolutely. But here's 273. Here's 373. 300 would be probably around here. 2 atm. If here is 1 and all the way up here is 218, the 2 is going to be very close to here. So we have to, where do these 2 points meet? They meet right here. And we can tell that in this section, this would be a liquid. So our answer is a liquid. Alright. I have a cup of water sitting in a room that is 350 Kelvin and 1 atm. If I kept the pressure the same, so the pressure is the same, still 1 atm, would the water boil if I increased it to 400 Kelvin? Why or why not? So again, I have a cup of water that's sitting in 350 Kelvin and 1 atm. So let's first find that amount. 350 is close to around here. Here's 273, here's 350, and 1 atm. So we're sitting just about here. Right? We're going to keep the pressure the same. So we're still at 1 atm. But now we are at 400 Kelvin. So here's 373. So 400's about here. We go to our new line. And now we are in the gas section. So yes, this water would boil if you change the temperature from 350 Kelvin to 400 Kelvin. Yes, this water would boil because the new temperature would put our water into the gas phase. Alright? So that is all that we're going to be doing for the regular chemistry. You're going to be getting another, some form of graph. You're going to get something like this and something like this. And I'm going to really ask, what are you looking at? What type of information? Can you read the axes? Can you find points on a graph and answer a question about that? Alright, so I'm going to move on to the Scholars and Honors Chem bit. So the Scholars and Honors Chem bit. The following calculations we did for the first quiz for the honors class. So this can be a good rehash for you. Or you could skip ahead for the honors kids until we get down to these questions. But for the Scholars kids, I do want to go through with this real quick. Alright, I'm going to show this on the calculator, the online calculator that looks like this, and I'm going to try my best to show it on the physical calculator. Alright, so we're going to continue. First, what is the energy of a photon with a frequency of 7.5 times 10 to the 5th hertz? So I give you these formulas up top here, and I give you the value of H, and I give you the value of C. You will get this on the quiz. I'm not going to have you memorize this. So our formula, E equals H. I actually have to insert into here. E equals H times our frequency, nu. So the energy of the photon. So we are looking for E. I give you H. 6 times 10 to the negative 34th. Sweet 34th. And I give you our nu here. Equals 7.5 times 10 to the 5th. This is really just, it capitalized it. Come on. 10 to the 5th. Awesome. So all we have to do here is multiply these two numbers together. That's it. So to do this, I'm going to first show on our calculator here. So I'm going to make my webcam a little bit bigger. Hello there. The first thing we want to do, we take, so I'm actually going to write this out, 6.626 times 10 to the negative 34th multiplied by 7.5 times 10 to the 5th. On our calculator here, looks like this. You're going to type out 6.626. 6.626. Now, this is when we do that E bit. Here's the second key. You hit this second key, one on the top left. Then you hit this key right here, right above the 7. It says X to the negative 1 on it. This key where my finger is. And you will get that E. It looks like this. And then you type in the power of negative 34. So what you have just written is 6.626 times 10 to the negative 34th. That is what this shows on this calculator. And then you multiply it by 7.5. You're going to press that E again. So one more time. The second. And then this button right above the 7. Here's the 7. This button right here. 7.5 times 10 to the 5th. There's my E. Press enter. Here's your answer. Trying to make this. I will have you round to 2 decimal places, just like the previous quiz. So your answer will be 4.97 times 10 to the negative 28th. Alright. 4.97 times 10 to the negative 28th. Please remember your units. We're dealing with energy. Our units are in joules. So I do want to show how to do this on this online calculator. This can be found at the top of your classwork section of the Google Classroom. I wanted to do this link as well, just so you can practice this at home in case you don't own one of these calculators. Alright? So, you would do something very similar. 6.626. This one has a dedicated EE button, so you don't have to press the second. It's going to show up as a lowercase e. It's still the same thing. Now, this calculator does not have the negative key. So, this is the negative key down here. So, just use the subtraction for this online calculator only. It will not give you a syntax error. So, oops, I forgot the E. Here's the E. Negative 34. Multiply this. What was our frequency? 7.5. E5. Looks just like this. This will give you the same exact answer. Okay? So I've gone over this multiple times in class now. I'm doing this again. I'm going to assume that you know how to do this going forward. How to put scientific notation into the calculator. So, I'm going to clear my screen there. A photon has an energy of 6.4 times 10 to the 14th joules. What is its wavelength? So, this uses both of these formulas here. I give you the energy. I give you that energy, and I want you to convert it into a wavelength. So there are 2 ways to do this problem. The first one is to convert energy into frequency, and then use that frequency to answer into the first formula to calculate the wavelength. Or you can also combine everything into one step. I'm going to show us how to do it. I'm going to show us how to do it both ways. So the first way. 1. We have an energy of 6.4 times 10 to the negative 14th joules. Here's our formula. E equals H times our frequency. You divide each side by H. This H cancels out. Should be an H. E over H equals our frequency. Alright, so this would be 6.4 times 10 to the negative 14th over 6.626 times 10 to the negative 34th. This will give you the frequency. I'm going to go type this in. I'll be right back. Okay, so plug this into my calculator. I'm going to ask for 2 decimal places, 9.66 times 10 to the 19th. And our unit of frequency is hertz. And then, what you can do now that you have this frequency, you can put our frequency into this formula. That one that we did last time. So, what we would get here, C equals lambda times nu, divide each side by our frequency. Frequencies cancel out. C over our frequency equals lambda. C, 3.8 times 10 to the 8th. Our frequency is what we just calculated right here. Alright, I'm going to go type this up. I'll be right back. Alright, so you put this into your calculator, and you get 3.11 times 10 to the negative 12. 10 to the negative 12, and because this is a wavelength, our units are in meters. Okay, that's the first way that you could do this. I do want to do the other way, just to, if you are feeling bold and adventurous, and you want to go ahead and do this. Alright, this is the bit with the transitive property. So how you do this? We have our two formulas. E equals H nu, and C equals lambda times nu. We have a nu, the frequency, in each of these equations. So what we can do, because we start with our energy here, we can isolate our energy or our frequency over here. So E equals H times our frequency, which means that, like we did last time, we divide each side by our E. E over H equals our frequency. Now, what we can do is we can take this E over H and put it right there. Replace this nu with this formula because of the transitive property. So C equals to lambda times E over H. Now we do have to do a little bit more of algebra to get this completely solved. This is a little bit more challenging just with the algebra. So what we can do for here, let's multiply each side by H. This cancels out our H. Alright, so we have HC equals lambda E. Now we have to divide each side by E. And we will get HC over E equals lambda. And then you can plug in those values. You can do 6.626 times 10 to the negative 34th times 3 times 10 to the 8th. All of this over, and I realize I should have put this somewhere else. That's alright. Over this energy bit here. Goes here. You could do that, and you would get this same amount here. So I just want to give both of those options. I'm going to leave this in there. I don't expect many of you to try that, but it is there if you so choose to. So this is the bit where the last few things for scholars, and then honors, you should know this as well. So how are energy levels quantized? So you should know what this means, and I tell you to check your notes if you're confused. Energy levels are quantized because an electron can only have a certain amount of energy. It cannot be somewhere in between. So what I mean by this, if we had our energy levels, if I said that this was 10 joules, this was 20 joules, and this was 30 joules, it's like we're playing like the skee ball or a target. If you have an electron here, like this, I'm going to use a different color for it. This electron has 10 joules of energy. This electron has 20 joules. It cannot be 15. It cannot be 14. It cannot be 13. Okay? It can only be this certain amount of energy. That's what a quanta means, or quantized. Alright? Going back here. Suppose you had a helium atom that looks like this. Is this atom in the ground state or the excited state? So, this is a little bit of an application from what we've learned previously. You should know that there are 2 electrons in the first ring. There are not 2 electrons in the first ring. There's 1 in this first, 1 in the second. So this is in the excited state because the ground state would have 2 electrons in the first ring. That's something that you're gonna have to remember. That we talked about that on our Quiz Plus. There should be 2 electrons in the first ring. Because there's not, this is in the excited state. This electron, this one right here, took energy to get that from the first ring to the second. What would happen if the electron in the outer ring moved to the first ring? If this electron went down to this first ring, it would release a photon of light. That's the big idea. And if you're seeing this after the flame test, you're going to see that that photon can be a visible light photon, that we can see it as a color. So that is all for scholars. I do want to get to the last few things for honors. Let me pull this back up. Alright. What is the photoelectric effect and how does it prove that photons are quantized? If you're stuck, check the notes/sides. So the photoelectric effect. That's that whole bit where if you have a piece of metal like this, if you have low energy waves, no matter how many low energy waves you throw at this thing, you could have 1 wave, or you could have 20 million, lighters on this piece of metal, it will still not release an electron. But when you have a higher wave, higher energy, you will start to get electrons that are released. We use the letter E to represent an electron. So what this means is that in order for an electron to be released, it must take a certain photon energy to actually release it from the metal. The energy does not add together. Having a continuous wave does not mean that all of those waves combine their energy. That's not how it works. It's only, is there enough energy in one photon, or is there not enough energy in a single photon? Okay? And just to complete, if you use, let's say, purple, the highest energy, hello? Did that just... Okay, so, I didn't get to finish my drawing, but when you have more energy, that electron that flies off has more kinetic energy. Alright? So photoelectric effect. Electric effect. So photons with not enough energy cannot release an electron from a metal. Only after a certain amount of photon energy will an electron be released. This shows that waves do not add infinite energy together. Rather, the photon either can or cannot release the electron. Right? More photon energy means more electron kinetic energy. It moves faster. Right? That's what I'm looking for with this one. Finally, we get to the last bit. An electron in a hydrogen atom jumps from n equals 3 to n equals 2. What is the wavelength that will be released by the resultant photon? And I give you the formula, and I give you the Rydberg equation here. The constant. So, how are we going to solve this one? First, n1, this number right here, that is always going to be the smaller number. I feel like I mumbled this in class, so I'm just going to say it's the smaller number. So that would be 2. So our equation is going to look like 1 over 2 squared minus 1 over 3 squared. Alright, so let's do this in a calculator. 1 over 4, you should know what 2 squared is, minus 1 over 9. I'm going to go to my calculator here. I'm going to be very meticulous about how I put this into the calculator. The best way to do a question like this is to actually do it step by step. Get this parentheses. Do the PEMDAS. Okay? So, we're going to take 1 divided by 4 minus 1 divided by 9. It's going to look like this. This will get you this value, 1.388888 repeating. So I am going to actually type this in. Alright, so you put this into the calculator and you get 1.3888. You know what? That is actually, I'm double checking myself. This should be 0.13888. My bad. Okay. So then you're going to multiply this number by our Rydberg constant right here. So you can take 0.1388, multiply this by 1.097 times 10 to the 7th. Alright, this is again using that scientific notation that we've been using a lot. You're going to put this in your calculator. And I'm going to put this in our calculator and get back with an answer. Alright, so I put this in the calculator, and this is what I got. So this is 1,523,611.111 repeating. So now, if we were actually to go through and do the math here, what we would have is 1 over lambda equals 1523611.111. Alright, so the way that we can do this, let's set this to an x. I'm going to set this to an x. So 1 over lambda equals x. We need to solve for lambda. How we're going to do this? We're going to multiply each side by lambda. These lambdas will cancel out. So we have 1 equals x times lambda. Now we need to get rid of the x. We divide by x on both sides. So 1 over x equals lambda. So our wavelength is 1 over 1523611.11. Okay? I'm going to put this in to our document and come back with an answer. So I did all that stuff. I did 1 divided by this number here. I get 6.56 times 10 to the 7th meters. So here's your answer. And we could actually go and check and see, is this part of the visible light? What color does this represent? But for now, I just wanted to do the calculation. We're going to get a little bit more into it. I'd probably have on a test, for example, okay, what color is this? Based off of your wavelength. Which of the 4 emission spectrums for hydrogen does this match up to? Something like that. But for now, this is what I'm asking for. Alright? So that's all for this quiz. It's a little bit different because we are doing the flame test, so we don't have that lab day to kind of go over and review. Last week, because of the way that the schedule was changed around, we had our block day on Tuesday, whereas you guys will get your flame test on Thursday, and then you're gonna have to study that night to prepare for um, the test. What I'm gonna do, and I'm gonna tell this now. It depends on when you watch this, but I'll tell you in class. I will do an office hours after school on Thursday, and maybe Wednesday as well, just to kind of go over stuff like this. Because no doubt you're gonna need help with this one. Okay, that's all for me.